Today I will present in this webinar how we capture, process, interpret and deliver drone-assisted outcrop 3D photogrammetry models at GSWA. So what are the advantages of capturing virtual outcrops, and why are drones so useful in geosciences and particularly in structural geology? Well, virtual outcrops are a great add-on to traditional fieldwork, and they allow us to extract more information from an exposure than we would from field observations alone. And this is particularly useful in complexly deformed terrains and where exposures are rare, which is the case in most regions of Western Australia. Virtual outcrops are fantastic communication tools to discuss and present observations and interpretations. They can be revisited in the office over and over again, and their interpretation can be updated based on new data. They can also offer a time series on deteriorating or ephemeral outcrops. And why drones? Well, they offer another scale of observation of geological objects and at a very high resolution thanks to the onboard high resolution camera. Probably one of the most valuable aspects of working with drones is that they provide a bird's eye view over geological objects, often too large for the geologist to fully grasp in the field, or too small to be imaged by geophysical datasets. When producing regional scale geological interpretations, the geologist looks at millimeter to tens of meter scale objects in the field, and back in the office we look at it in sections to further characterize our field observations, but then to produce maps we commonly jump straight to the scale of the aeromagnetic data, which is in the order of hundreds of meters and up to the orogeny scale, and by doing so we upscale our field observations by at least 2 orders of magnitude, if not 3 or 4. So drone imagery here reduces by at least 1 order of magnitude, and commonly by 2 or 3 orders of magnitude, the uncertainty due to upscaling, and therefore can help interpreting the aeromagnetic data more confidently. These are the drones that we currently have in our possession at GSWA, a DJI Phantom 4 Pro Obsidian, and we have recently acquired a Phantom 4 RTK. Both of them fall into CASA's very small RPA category, and both have a similar onboard 20 megapixel gimbal camera. Obtaining a Phantom 4 RTK is about improving drone accuracy to achieve centimeter level absolute accuracy on imaged metadata and of the resulting photogrammetry models. I usually carry this drone in the vehicle when I go out mapping, and I have it ready to capture outcrops that deserve a bit more attention. Then I start setting up the scene for capturing photos that will eventually be used to produce a realistic 3D model of the exposure using a photogrammetry workflow. Then I choose and delineate the area that I want to cover. You can see here the drone landing pad. This is where I will set up the drone. And then I place a number of scale bars scattered over the whole exposure. They are 60 centimeters long by 40 centimeters. I place them horizontally on the ground, and I orient the red end of the scale bar pointing towards the north. In this example, I wanted to be able to see from above the relationship between the mafic boudin here within the surrounding granitic gneiss, and you can see that there is in fact a series of these mafic boudins scattered throughout the exposure. The bird's eye view offered in this end result model shows the spatial arrangement of the mafic boudins within the granitic gneiss in a way that was impossible to observe from the ground. Once I have set up the scene, I then use the DJI Ground Station Pro application to design the automated flight path that will dictate where the drone goes, capturing georeferenced overlapping photos of the area of interest. At this stage, you need to make sure that the resolution of the end model will resolve the geological features that we are trying to capture. In our case, since all the camera specifications are fixed, the ground resolution is only dependent on the altitude of the drone and of the photo captured. So once you're happy with all the settings for the flight, then you press the start button and the drone goes mapping, capturing photos along the flight lines. Then the processing part. Typically a survey will contain hundreds of photos that you then import into your favorite photogrammetry software. Here I use Aegisoft Metashape Pro, and the first step is to check the quality of the photos. Then you can simply follow the photogrammetry workflow provided by the software. In the first step, the software aligns the photos and creates a sparse point cloud. Each point is located in 3D space and contains an RGB attribute, so the point cloud is colored up. You can see here the locations and angles from which the photos were taken. Then the next step is to build a dense point cloud. In this example, we go from 200,000 points for the sparse point cloud to over 3 million points for the dense point cloud, which is actually not that many. We commonly create dense point clouds with over hundreds of millions of points. Then you can create a mesh at a resolution of your choice. Here I chose 500,000 faces, which is relatively coarse but sufficient for what I wanted to represent. Finally, the software creates a texture draped over the mesh, and this is your realistic 3D model. Then you also have the option of creating a tiled model for enhanced visualization speed at full resolution. From these 3D datasets, you can create 2D images. Here I created a DEM from the dense point cloud, and on the right hand side is a high resolution 2D orthomosaic. All these photogrammetry datasets can then be exported as various formats. I use LAZ format for my point clouds, OBJ for the 3D models, and TIFF files for my orthomosaic exports. So here are a few examples, a few snapshots from various models. You can see here the difference between the sparse point cloud and a dense point cloud for the same object on the top left and top center of the slide, and examples of high resolution models. You can see the highly realistic representation of my hammer and the carry case in the tiled model on the top right, and at the bottom of the slide you can see examples of screen captures from high resolution orthomosaics and also from another tiled model. Then comes the interpretation phase. I use the 2D orthomosaics that I import in ArcGIS to create a 2D map interpretation of the outcrop, here using an example of an exposure along the Fraser shear zone in the East Albany Fraser orogen. I'll draw the form lines, the lithological boundaries, and create a 2D structural and geological interpretation. But where this starts to become really powerful is that once you have interpreted a few of these key exposures, you can then place them all together in the greater regional context. You can start comparing the deformation history along this particular shear zone, as shown in this example, but then you can extend this approach to cover an entire orogen and make regional scale correlations between outcrops and your aeromagnetic data, for example. In 3D space, I use Cloud Compare and the Compass plugin for semi-automatic mapping of structures. Once you have loaded your 3D colored point cloud into Cloud Compare, you can create geo-objects that you will want to measure. Here I have created a northwest trending fracture set for this example. You can activate the compact mode to start measuring. Here are some of the northwest trending fracture planes that I want to measure. And you can either choose the plane tool here to directly measure the orientation of planes in the model. I zoom into the area of interest. You can increase or decrease the size of the circle and fit a plane through the points captured into the right circle. The normal plane, or the normal to the plane, is shown, and the dip and deep direction of the plane is labeled. Another way of measuring planes is by using this trace tool and fit a plane through the series of points. It allows you to map features semi-automatically by choosing points of similar color. So here I've chose point of darkness, and you can click in various points of the model, and semi-automatically it will go between points of darkness between the clicked points. You can adjust the line, and then once you're happy with it, you can OK it, and it will create a best fit plane through this series of points. And you can see that the two planes measured by both methods have very similar orientations. Relatively quickly, you can generate a large number of measurement data of various fabric elements over the whole model area that you can then export to your favorite StereoNet software for further analysis. And similarly, you can produce this type of structural analysis for all of the models that you have available across an entire orogen to further quantify the map, the 2D map interpretation that I've just shown before. To go even further, you can then export all your measurements in a 3D modeling software to further characterize the geometry of your structures in your exposure. Here I am showing the example published by Folger and Cruden in the Journal of Structural Geology in 2016, where they have used CladCompare to create structural data from their georeferenced dense point cloud. They have measured over 2,000 bedding planes, which they then extracted and imported into the 3D implicit modeling software Leapfrog to model the folded surfaces of this Cape Liptrack fold stack exposure. Okay, so to summarize where we are at in this presentation, here is a flow chart that summarizes GSWA's workflow towards capturing, processing, and delivering photogrammetry data. I have talked about the capturing, processing, and the interpretation parts on the left-hand side of this flow chart. The next step is how do we deliver and present the data and interpretations to the customer. So one of the ways that GSWA has to deliver data to the public is through the release of data packages collated in USB flash drives for a given project. Then I will show you GSWA Sketchfab page, which is an online repository of 3D models. And in the near future, we will also provide access to all these data and interpretations through GeoView, which is our online platform for viewing, interrogating, and downloading GSWA's geological data and interpretation. So here is the example of the East Albany Fraser GIS package that we have released in 2020. In the ArcGIS project, you can plot the locations of the drone models, symbolized here by a black swan with 4 propellers. And in map view, you can load the 2D orthomosaics. They are linked to the directory on the USB drive under the photogrammetry folder. In this directory, you will also find the 3D point clouds and the 3D models. We have also provided the freeware CladCompare and the viewer as part of the package so that people can play with the 3D data. And if you click on one of the black swan symbols, it will direct you to a URL link towards the 3D model in Sketchfab. So here it is. This is our GSWA Sketchfab page. You can use the QR code on the top right of the slide that will direct you to this web page. We currently have 125 followers, and we have several models that have been seen over 1,000 times. We have a total of 56 models currently loaded in Sketchfab. I have organized them in various collections, here based on geological provinces, and in the near future we will also include our geoheritage sites as well as our collection of 3D fossils. If you click on one of the models, this is what will open, and in Sketchfab we have the possibility to annotate the models. So I put here information about scale and orientation of the models, information about lithologies, information about the nature of the gneissic layering, informations about the formation history, and various other structural informations. Eventually we will also put this data out on GeoView. This is currently work in progress, and if you are familiar with the geology of Western Australia, you will recognize here on the diagram on the right the outline of the Yilgarn Craton and the location of all of the models that we currently have in Sketchfab. Most of them are in the East and West Albany Fraser orogen, but we also have a few in the Lewin layer and along the Darling Fault, and several models within the UNME terrain, particularly around Yalgoo Dome, and a few also in Kalgoorlie and Kambalda region. And we keep on uploading data to Sketchfab and to this map. And I will leave it here. Thank you very much